All right. So testing hypothesis about population variance, one sample. In order to test this hypothesis, we're going to use a chi-square distribution. The requirements, we have to have the sample that is simple random, and the population must be normally distributed, no matter what the sample size is. Same as, notice that these patterns are coinciding with the patterns for the confidence interval that we just learned. We use the Z distribution or the normal distribution for confidence intervals of proportions. We use the T distribution for confidence levels of sample mean, and chi-square distribution for confidence intervals for variances or standard deviations. So it's the same for hypothesis testing. It's not different. Okay, so once you learn that for unit, what was it? 10, I think, you're going to use it here again. So we're using a chi-square distribution for testing hypothesis about population variance. And this is the formula that we use to calculate our test statistic. Let's take a look. So here's our problem. Says the Stewart Aviation Products Company uses a new production method to manufacture aircraft altimeters. A simple random sample of 81 altimeters is tested in a pressure chamber, and the errors in altitude are recorded as positive values for the readings that are too high or negative values for the readings that are too low. You may assume that the distribution errors in altitude is normal. So we are dealing with the normal distribution that speaks to our requirements. The sample is a random sample, the population must be normal. So we do have it here. The sample has a standard deviation of 52.3 feet. At the 0.05 significance level, test the claim that the new production line has errors with a standard deviation different from 43.7 feet, which was the standard deviation for the old production method. If it appears that the standard deviation has changed, does the new production method appear to be better or worse than the old method? Okay, so again, our first objective is to identify the claim. And it usually comes after the significance level. Test the claim that the new production line has errors with a standard deviation different from 43.7 feet, which is the old one, standard deviation. Okay, so how do we write this in as a mathematical expression? All right, so different from means not equal to. Different from means it could be less than or it could be greater than. So this is new. This is going to end up in the two-tailed test. And how do we deal with the two-tailed test? How do we figure out the p-value, and how do we figure out the critical value for the two-tailed test? That's going to be new. All right, besides the fact that we're testing standard deviation now. And remember that the standard deviation of the population is a sigma. So sigma is different from 43.7 feet, right? Where does it go? it goes into the alternative, our golden standard. Okay, now the null will say that the mean is equals to 43.7. All right, so what's the significance level? They told us significance level is 5%, so alpha is 0.05. The test statistic. Here's how we calculate. This is the formula for calculating the test statistics. So we need the standard deviation of this from the sample. We need n. Do we have that information? We have a random sample of 81 altimeters, so n is 81. And what about standard deviation? Right here. So S is 52.3. So we have everything that we need in order to calculate our test statistic, chi-square. So chi-square is 52.3 squared times 81 minus 1 divided by, in the formula we have a sigma squared on the bottom. This is where the sigma is. So we're going to use 43.7 squared. What is it equal to? I got 114.586 rounded to 3 decimal places. All right, so now what about the p-value and the critical value? Well, that comes from the chi-square distribution. So let's take a look at that. Now, since this is a two-tailed test, right? We're trying to prove that sigma is not equal to 43.3. So this could be sigma is greater than 43.7, or that means that it could be less than 43.7. So this means that we have a two-tailed test. If our value falls to the very left, it's gonna prove that it's not equal to, but specifically that it's less than. And it could fall on the very right hand side, and that will prove that sigma is greater than 43.7, yeah, not equal to, specifically greater than. But this also means that our alpha is going to be split into two tails. So we're gonna have 0.025 on one side and 0.025 on the other side. So we're gonna have two critical values here. So let's go ahead and figure out the critical values. So if we go to our StockCrunch, we're gonna open calculators this time. We're using the chi-square distribution with the degree of freedom 80, because our sample size was 81. All right, and now if we're gonna put in 0.025, the area under the curve in the left tail, and that gives us the critical value of 57.153. What about this value in the left tail? We're gonna switch the sign and switch our area back to 0.025. And this is what we got. We got 106.629. That's if you were asked to find critical values. All right, so those would be our critical values. What about the p-value? Well, the value that we found as a test statistic was 1.14. Okay, so I'm gonna put it in for the chi-square value. 114, the value of our variable, 0.586. I don't know if it's the right tail or the left tail, so it looks like it's the right tail. So the area there is 0.006. So this p-value right here is 114.586. Okay, now it seems like we have enough information to make our conclusion already, because we could see that our test statistic, actually that's the test statistic right here, of 114.586, and the p-value that corresponds to that test statistic is actually 0.0068. All right, so that little area right there is 0.0068. So, and this is enough information to actually make our conclusion already, because we see that our test statistic fell into the critical region. It's to the right of the critical value of 106.629. So we could say that this is what's happening. The true standard deviation is actually greater than 43.7. We can reject the null, support the alternative. But if you're asked to actually find the p-value, because it is a two-tailed test, you have to reflect this area to the other side as well. So the p-value for this test is going to be 2 times 0.0068, just because it's a two-tailed test. Okay, so if it was a one-tailed test, you wouldn't have to multiply by 2. So our p-value is 0.0136. All right, if you're asked to find a p-value. But like I said, the information that we got was enough to make the conclusion already. And our conclusion would be to reject the null. I don't have room here. So reject the null and accept the alternative. We did not get, we did get enough support. So for the interpretation, again, we're going to start with the significance level at 5% significance level. So let's start over. At 5% significance level, we have sufficient evidence to support the claim that the new production line has errors with a standard deviation, and not just not equal to, but we can also say that it's greater than 43.7 feet. So the standard deviation is greater than 43.7 feet. Think about it. If you're in charge of making a decision whether to buy this new equipment or not to buy the new equipment, what would you decide? if your standard deviation is greater than the old equipment produced, then is it worth to invest into getting this new equipment if actually the accuracy of it is less? Like the greater standard deviation means less accuracy. So would you invest into upgrading your equipment? You probably would be better off using your old equipment because it has a lesser standard deviation. Okay, so that's how the test of hypothesis for population variance work. We also discussed a two-tailed test in this context. And please proceed to the next video where we're gonna summarize what we learned about testing hypotheses.